Today, we're excited to present our project about the word-level and pose-based sign language interpreter. This is our AI for Good solution, designed to bridge the communication gaps for the deaf and hard-hearing community. Let's dive into why this project matters, how we built it, what we've achieved, and the challenges we faced. Communication is a fundamental human need, but according to WHO, there are over 1.5 billion people today experiencing some kinds of hearing loss, a number expected to rise to 2.5 billion by 2050. And the only way that these people use to communicate with the rest of the world is to use sign language, a visual means of communication using hand gestures, facial expressions, and body movements. And for these deaf individuals, digital spaces like virtual meetings or online classes often exclude them due to a lack of accessible tools. Additionally, many existing sign language translation solutions rely on specialized hardware like gloves or glasses, which is expensive and not widely accessible. Our project aimed to change that. You can imagine a world where deaf individuals can communicate seamlessly in any digital space without barriers. That's the vision we've worked for, using AI to make a real difference. Our goal was to create an affordable, accessible solution that translates American Sign Language into English text in real time. So what impact does our project bring about? Firstly, it promotes accessibility by eliminating the need for specialized hardware. Here, any standard webcam can be used, making this solution cost-effective and widely available. Secondly, it enhances communication by providing real-time captions, which can be integrated into platforms like Google Meet, used in social interactions, whether it's a virtual classroom, a job interview, or just a casual conversation with friends. Thirdly, we focused on word-level, pose-based interpretation, going beyond simple fingerspelling for only alphabet characters like previous projects, to capture the true essence of sign language communication. And most importantly, this project contributes to social good. By breaking down communication barriers, we reduce isolation and foster inclusion for the deaf community, empowering them to engage fully in a hearing world. We believe communication is a human right, and our project isn't just a tool, it is a step toward a more inclusive society. There is a previous work addressing a problem quite similar to ours: sign language recognition and sign language translation. They used a spatial temporal multi-cue, or STMC network, to extract features from multiple visual cues: face, hand, full frame, pose, and a transformer network for sequence learning and translation. The problem is that their STMC is for video-to-text translation, unlike our approach, pose-to-text, for easier processing. Moreover, their model is not open source, so we can't have a look for customization. A significant milestone occurred when I discovered the Google Isolated Language Recognition (GISLR) competitions on Kaggle, where participants utilized landmark data extracted from MediaPipe to predict approximately 250 glosses. I decided to adopt the best solution from this competition for my used dataset. Now let me walk you through our solution. Overall, our interpreter will take a video of someone signing in ASL, processes it, and outputs natural English captions in real time, all using just a standard webcam. Here's how it works. First, instead of processing heavy video data, we take a pose-based approach. We capture video from the webcam and use Google's technology called MediaPipe to extract 180 lightweight landmarks per frame, focusing on hands, upper body, and facial features. This approach is not only faster, but also robust against diverse conditions, like varying backgrounds or skin tones, ensuring reliable performance in diverse settings. Next, we adapted a hybrid convolution 1D transformer model, the best solution from the GISLR competition, to capture hand positions and extracts movement patterns. This model recognizes the sign and predict glosses, like go or dance. It achieved a top 5 accuracy of 86% on the WLASL 100 dataset we used. Then, we pass these gloss predictions to a gloss-to-text module, which uses GPT-4o Mini through OpenAI API to translate a sequence of signs or glosses into natural English sentences, such as, "Let's go dance." But there is still another problem here. ASL's unique syntax posed a challenge. Glosses don't directly map to English sentences. They often lack articles and follow a topic-comment structure. We tackled this by designing a smart prompt for GPT-4o Mini, allowing it to form meaningful combinations from multiple gloss predictions, resulting in more natural translations. Building this solution wasn't without its challenges. Our most major problem was the sparse dataset. The WLASL dataset we used has 2,000 classes, but only 4 to 6 examples per word, making it tough for our model to learn effectively. We overcame this by applying data augmentation techniques like rotation and zooming, and by adapting a best model from the Kaggle competition, which boosted our accuracy. However, our top 1 accuracy was still just 61%, which wasn't ideal for reliable translation, so we temporarily innovated by using the top 5 predictions, which has 86% accuracy. Another challenge was achieving real-time performance. Through optimization, we already able to reduce our post-to-gloss model latency to under 1 second by using the key points and TensorFlow Lite, ensuring a smooth user experience. However, the current translation using GPT can be slow, like still around 3 seconds, making the whole process will cost the same number with the length of video. These challenges pushed us to think more creatively, to find a better solution. For future work, we plan to use larger and more balanced datasets with a continuous approach. Moreover, our current moderate results are not exactly due to the model. It's also about how we handle a sequence of frames, and this requires the development of another model to perform the temporal segmentation to detect when a sign starts and ends, which we are currently put in the out-of-scope section in the product requirements. We also plan to further improve the gloss-to-text module by utilizing the top N parameter that we designed to return different glosses with scores, and letting the GPT decide the translations. This idea is quite similar to beam search. Thank you for watching this video about our word-level and pose-based sign language interpreter project.